Hello and welcome to the Deep Sea podcast, Pressurised, a short, punchy version of our main feed that gets right to the scientific point. If you like what you hear and you'd like to hear the full episode, you can find it in the same feed. And now, to get right to the point.
So Tom's not with us this month because at long last he's finally got back out to the deep blue. He's away doing a deep sea fishing expedition on the Bounty Trough, I believe, south of New Zealand. So he's not available, but he will be chiming in with some news from his travels. So as of now, this podcast is mine, all mine, nothing to do with Tom. But if anything goes wrong, it's still his fault. So that's the T's and C's out of the way. And given that I'm basically freestyling and free-falling this entire episode, I've not had a rant in a while. I haven't had a proper rant in a while. I've only had little micro rants, I would say. If you go back to some of the early episodes, I do have beautiful big mega rants. So I've prepared another rant, and that rant is about when does the sea become deep sea and why we should change that. Let's talk about when does the sea become deep sea, or rather, when should the sea become deep sea? So over 30 years ago, eminent deep sea biologists John Gage and Paul Tyler published a classic textbook, Deep Sea Biology, A Natural History of Organisms at the Deep Sea Floor. Early in that book, they asked a solid opener, what is the deep sea? And they explained that ask virtually any deep sea biologist and you'll get a slightly different answer. In most deep sea literature, the deep sea is considered to be the oceans deeper than 200 metres. Often this is given with a caveat of it also being beyond the edge of the continental shelf that bounds the periphery of the ocean basins. It is also said that the upper limit can be based on the depth of the mixed surface layer, temperature, light penetration, or the depth below in which plant life is largely absent, which the latter two suggesting the limit to photosynthesis. A biological transition from shallow water fauna to the shelf to the deep sea fauna has also been defined for some time, or the combined descriptor of penetration of sunlight, a covariant of depth, and by the associated fauna. But the general consensus is that the deep sea is the ocean beyond the shelf break at depths deeper than 200 metres, underlying the photic zone. So establishing a solid definition requires a consensus for coherent communication, and that language use is a matter of social consensus, and that we delegate stronger authority to the use of certain terms to relevant authorities. This is why us as scientists need to clarify what we actually think the deep sea is. The issue with the term deep sea is that the word deep is very subjective, and it can mean different things in different contexts. For example, the deep end of a swimming pool can be 3 metres. Deep sea sports fishing is generally fishing greater than 30 metres. Deep sea fishing industry, generally in the top 1,000 metres. Deep sea mining is 4,000 to 6,000 metres. Challenger Deep is 11 kilometres underwater, and it gets really muddy when you start looking at deep space. Deep, by definition, simply means extending far down from the top of a surface, and far simply means a great distance, and great means unusual or comparatively large in size. The term is used entirely in context of the activity in which it's being used. While acknowledging times where something was once thought too deep, in hindsight it's no longer sufficiently challenging to feel unreachable. So historically, the definition of deep sea has been argued based on what was known at the time to be considered deep. In the book Fathoming the Oceans, there's a story there that regales correspondence from 1869 where J. Gwynne Jeffreys wrote to the journal Nature claiming that 10 fathoms, which is 18 metres, was too shallow for the term deep sea, which had apparently been the definition since the 1840s. He claimed that 50 fathoms, which is 91 metres, was a better delimiter for the deep sea based on the depths that were readily being sampled at the time. 8 years later, he had further refined it to abyssal for anything from 1,000 fathoms, which is 183 to 1,829 metres. This is arguably the first mention of what is now the bathyal zone, and therefore the defining the upper limits of the deep sea, approximately 200 to 2,000 metres, albeit rounded following a conversion from fathoms, refers to the neritic zone, its depths less than 200 fathoms, and bathyal, its depth between 200 fathoms and 2,000 fathoms. The famous Edward Forbes described his regions of depth. The first was the littoral zone for the space between the tide marks. The second was the circumlittoral or laminarian zone, coined after the tangles of seaweeds. And the third was the median coralline zone, a depth that occupied between 10 and 50 fathoms, where seaweeds were mostly absent. And the fourth region was the inframedian, a region of deep-sea stony corals. And the fourth was the abyssal region, which can be scarcely said to be developed within the British area. Therefore, Forbes' depth definitions were simply based on local biodiversity surveys around Europe. So regardless of how the exact depth was established, it appears clear that it was based upon a less or greater than 100-year-old European or North Atlantic-centric idea of waters that extend beyond the continental shelf in those areas. Defining rules to the natural world as simply as what is deep and what is not deep will always run into exceptions and variability that may lead to questioning the value of the rule at all. For example, 200 metres as the limit to plant growth is quickly challenged since seaweeds have been found as deep as 265 metres, albeit most are less than 200. Solar light penetrates much deeper into the ocean than 200 metres by another 800 in some places. 2.7 million square kilometres of continental shelf around Antarctica tends to be closer to 450 metres, over twice the norm of 200. And in the absence of continental shelf on places such as islands and atolls, the 200-metre contour is often ignored altogether when defining transitions. Therefore, consistency in nomenclature when defining ocean realms or zones where the issues lie. So let's think about the continental shelf thing. The continental shelf only accounts for 8.9% of the 32 million square kilometres of ocean. The significance of the 200-metre contour is greater in the western regions where early marine science emerged than others across the globe. Using some stats from a paper by Harris et al. 2014 on the global area of the undersea geomorphology, it was found that as a percentage of surface area, the percentages in the aforementioned western areas, the North Atlantic, Mediterranean, Black Sea, were 16 and 23% respectively. These are in contrast to the Indian Ocean, 5.7%, South Atlantic Ocean, 5%, North Pacific Ocean, 7.5%, South Pacific Ocean, 2.9%. And there are, however, large percentages in the polar regions with 51%, 13%. So basically, there's far more continental shelf around the North Atlantic, Mediterranean, Black Sea than there are in other oceans. The Arctic arguably played an important role in the early Western exploration by bounding the North Atlantic Ocean between North America and Europe. The combined continental shelf area of the Arctic, North Atlantic, Mediterranean, Black Sea is 14 million square kilometres. Therefore, 45.7% global shelf area is situated in these areas that account for just 16.8% of the oceans, but happen to be regions that have a strong legacy in marine science at the time of defining basic terms of oceanography. Gunther and Deckard, 1956, described the deep sea as driven by geomorphology where, down to 200 metres, the bottom has a relatively gentle gradient, and that below 200 metres, the bottom generally falls more steeply. But what they are describing here is the North Atlantic, and not necessarily a global scenario that is easily recognised around the Pacific Rim or global south. In the inhabited global south, the South Atlantic, South Pacific, and Indian Oceans, which is 55% of the ocean combined, the continental shelf accounts for just 4% of that combined area, or 26% of the global shelf area. Alternatively, the combined shelf area of the North and South Pacific represents just 5.1% of the area. Furthermore, the continental shelf around Antarctica is much deeper than other continental shelves, with an average of 450 metres, which can extend over 1,000 metres, and is also unique in that some of the shelf area features glacially excavated, over-deepened inner basin that can be over 1,500 metres deep. On average, the Antarctic shelf is almost twice as deep as other continental shelves elsewhere. So the 200-metre shallow to deep boundary is likely an artefact from the days of early scientific exploration originating from around the North Atlantic and does not offer any practical bathymetric or geomorphological boundaries in most of the rest of the world. Although there are large areas of shelves in other areas, for example, Australia or Argentina and so on. So perhaps light would be a major consideration. Solar light is often posited as a driver of marine diversity and biomass due to photosynthesis-derived phytoplankton increasing available energy in the upper ocean that indirectly supports a complex food web that supports the deeper waters below. At 100 metres below the surface of a clear ocean, the quantum spectrum of daylight narrows significantly and becomes much dimmer, declining by about 2.6 log units, but can vary considerably in different clarities of ocean water. Below 100 metres, coinciding with a decrease in plankton and suspended organic matter, light intensity declines by about 1.5 orders of magnitude for every 100-metre water depth. By 600 to 700 metres, it reaches starlight levels during day. Beyond 1,000 metres, daylight no longer penetrates sufficiently to be significant to deep-sea animals. The seawater has a higher refractive index than air, which results in the entire 180-degree dome of the sky being compressed underwater to a 97-degree cone known as Snell's window, which is always brighter than surrounding spacelight. Although it is dominated by the position of the sun and the surface layers, its dominance declines with depth, disappearing altogether below the so-called asymptotic depth at approximately 400 metres in the clearest ocean water, albeit shallower and more turbid water. Therefore, solar light seems to be quite significant at twice the depth of what we're calling the deep sea. So let's think about where shallow species go deep. Many large marine taxa that are often synonymous with the surface layers are known to make excursions to the deep sea beyond 200 metres. For example, deepest Arctic whale is 1,592, deepest sperm whale is over 1,000 metres, deepest beaked whale is nearly 3,000 metres, dolphins are known to go to 300 metres, great white sharks 1,000, and so on and so on. Even reptiles and birds are known to cross the 200-metre contour. And I was quite surprised to learn that sea snakes go to 250 metres. These are examples of species most often considered surface-dwelling species that happen to make brief deep dives or excursions greater than 200 metres. Other uses of deep sea by shallow species in inverted commas, such as the most dominant member of the zooplankton, the copepods, is diapods, which is a kind of dormancy that is temporarily initiated in direct response to unfavourable environmental conditions to thrive in high latitude environments. To access areas where temperatures are generally colder and predators are less abundant or absent, diapause is initiated by a vertical migration to depths of several hundred to several thousand metres. There was a study that reviewed 6 Pacific species, 4 Atlantic species and 1 Southern Ocean species, and reported that all but one had a diapause range of more than 200 metres. Therefore, the importance and abundant surface-dwelling groups such as marine zooplankton are using the deep sea for a significant phase of their life history. And so in addition to shallow water species that dive deep or temporarily diapause at depth, there are also species commonly associated with being shallow that have depth ranges that extend beyond the 200-metre contour. Of the top 10 most commercially landed wild fish species identified by the FAO, only 2 of them are known exclusively from less than 200 metres. The rest transcend this magical 200-metre deep-sea boundary. For example, the Alaska pollock, the skipjack tuna, Atlantic herring, chub mackerel, the yellowfin tuna, the Chinese anchovy, the large-haired hairtail, and the Atlantic cod. These are all regularly found beyond the 200-metre limit. So what about when deep-sea species go shallow? The deep pelagic zone greater than 200 metres contains almost 95% of the ocean's volume. Diavertical migration is ubiquitous across the mesopelagic taxa. Mesopelagic fishes are among the most abundant marine organisms on Earth and are small and usually found at depths between 100 and 1,000 metres. Most mesopelagic species make extensive upward migration into the epipelagic zone during the night and thereafter migrate down several hundred metres to their daytime depth. Phytophid larvae remain in the epipelagic zone, which is less than 200 metres, and then move relatively to deeper depths to adapt to their later adult life in the mesopelagic zone, after which most species start vertical migration. Our friend of the podcast, Tracy Sutton, once stated that with a distribution range of 200 to 1,000 metres during daylight, the mesopelagic fish's nocturnal migration would be considered an upward flux into the epipelagic. This suggests that the deep mesopelagic is a fundamental element of the ecology of large epipelagic fishes, and the epipelagic is therefore integral to the ecology of nearly all mesopelagic fishes. This means that the mesopelagic fishes, amongst the most abundant marine organism on the planet, are neither shallow nor deep-sea fishes, but rather utilised at the top 1,000 metres. So what about depth ranges of common marine taxa? In addition to shallow water species going deep and deep species going shallow, and many marine taxa that are quite familiar in our daily lives extend far deeper than is generally appreciated. For example, marine groups such as the cephalopods are all found well below the 200-metre mark. Even cuttlefish at 600 metres, nautilus at 700 metres, vampire squid 5,000, squid 6,000, octopus 7,000. Other mollusks such as snails and clams are known from over 10,700 metres and sea slugs from 4,400 metres. Many orders of cnidarians are known from hadal depths, with hydrozoan jellyfish now known from over 10,000 metres. Sharks, rays, chimeras are found beyond 3, 4 and 3,000 metres, respectively. Jawless fishes such as the hagfish can be found at 3,000 metres. Of course, bonyfish can be found over 8,000 metres. Many kinodorms are represented at hadal depths, with sea stars to nearly 10, brill stars to 8.5, urchins to 7.5, sea lilies to nearly 10, and so on and so on. At the taxonomic class level, there are very few examples of those who do not use the deep sea at all. Someone else who uses the deep sea is us. So what about the industrialization of the deep sea? Another aspect to the subjectiveness of the term deep is how out of reach and difficult to access is it really. Here we can think about how much access we have to depths greater than 200 metres by using various industrial activities. For example, deep sea fisheries. Deep sea fishing was once a very challenging and dangerous activity, but not so much in modern times. There are 72 species or species groups being caught primarily with bottom trawls, mostly at depths greater than 400 metres. There was a paper found that the most fished and vulnerable deep-sea fishery species were the Greenland halibut, which go down to 1,000 metres, orange ruffy, also 1,800 metres, red-nosed grenadier, 1,200 metres, slender armorhead, 600 metres, Patagonian toothfish, 1,500 metres, blue line, 500 metres, and the long-nosed velvet dogfish, 1,500 metres. These fisheries are occurring well within the deep sea and demonstrate an intrinsic, albeit negative, link to the deep sea, irrespective of what we may consider to be deep. However, the vast majority, in terms of catch weight landed, is generally in the top 1,000 metres. Furthermore, the industrialisation of fishing fleets has resulted in bottom trawling on the continental slopes, reshaping the actual seafloor over large spatial scales. Trawling induced sediment displacement and removal from fishing grounds reduces seafloor complexity, smoothing it over time. Papers have anticipated comparable effects on the deep-sea floor by trawling to those generated by agricultural ploughing on land. In the Mediterranean, commercial trawling between 200 and 800 metres is estimated that the daily amount of organic carbon removed by trawling could be as high as 60 to 100% of the input flux, resulting in the degradation of sedimentary habitats and a significant decrease in and slower organic carbon turnover, therefore reduced biofauna abundance and biodiversity. There are studies that conclude that commercial deep-sea trawling represents a major threat to the deep-sea ecosystem at the global scale, but albeit largely within the top 1,000 metres. So the deep sea is not only a place to extract food, there is also an emerging industry in Asia that promotes the drinking of deep sea water for health benefits. There are papers that describe the health benefits of water to which a mineral extract obtained from the deep sea water is added, where it is defined as seawater from a depth of greater than 200 metres. It is thought that drinking deep sea derived mineral water could have numerous health benefits, including improving gut ecosystem and beneficial effects on intestinal health, and possibly alleviate obesity and diabetes and a range of other benefits. Who knows? In these studies, the water is actually pumped from a depth of 1,100 metres, around 18 kilometres off South Korea. The usage of deep sea water is an emerging industry, with some commercial brands boasting their deep sea water-based drink is concentrated from water pumped from 662 metres off Taiwan. This particular site has inlets 600, 660 and 710 metres deep. It is also emerging in Japan with great economic values worth billions of dollars. The United States also extract deep water from 600 metres, 670 metres and 900 metres deep off Hawaii to applications for bottled drinking water, agriculture, pharmaceutical and cosmetic products. There was even a Japanese journal dedicated to research into applications for deep sea water that published from 2000 to 2018. In many regions of the world, increasing water demands and diminishing groundwater supplies are prompting a greater reliance on desalination, as desalination water is expected to play a pivotal role in narrowing the water demand supply gap. As the production of desalinated water increases, methods to make the industry more efficient are being sought. One issue of efficiency is that of entrainment of marine organisms that can be substantially reduced or eliminated by placing intakes away from biologically productive areas, such as in deeper water farther offshore. Such intakes are supposed to be as deep as 600 metres. Another global industry present in the deep sea greater than 200 metres is the oil and gas industry. There are currently an estimated 12,000 offshore platforms and 180,000 kilometres of subsea pipelines. Furthermore, offshore marine renewable energy developments are likely to increase the amount of subsea infrastructure over the next 20 years. Although most platforms are situated between 30 and 150 metres of water on the continental shelf, there is deep water greater than 200 metre productions in areas such as the Arctic, North Atlantic Ocean, East and West Africa, Gulf of Mexico, South America, India, Southeast Asia and Australia. The majority of these are in water depths of less than 1,000 metres. Although ultra-water greater than 1,000 metre production does occur, it's still in its early stages and limited to areas such as the Gulf of Mexico, sometimes West Africa. Most deep-water fixed platforms in the Gulf of Mexico are located across the edge of the continental slope at depths up to about 400 metres. Here, approximately half of the fixed platforms are in 120 to 150 metre depths, with the remaining in approximately 150 to 300 metre depth. Only 6 fixed platforms reside in depths greater than 300 metres, and some floating platforms are located throughout the region in depths of 500 to 3,000 metres. So in modern times, we're readily fishing the top 1,000 metres. We're reshaping it with bottom trawls. We're drinking water from it. We're extracting hydrocarbons from it. Our most recognisable surface fauna, including air breathers, are utilising waters greater than 200 metres. The largest marine biomass is largely confined to the top 1,000 metres to migrate, while plankton use the top 1,000 metres as overwintering refugium. None of these excursions, migrations, or anthropocentric activities were known or were occurring at the time the deep sea was considered to begin at 200 metres. So I think when you start putting all this together and you think about subjectiveness of the word deep, deep means it's kind of out of reach. It's a place which is quite difficult to get to, and that was once true. And the 200 metre mark being associated with the continental shelf is something that which is primarily driven by the early marine scientists operating around the North Atlantic. I propose that the deep sea should really start at 1,000 metres, because at 1,000 metre, it does become quite challenging. And if we're regularly fishing and eating and drinking and extracting stuff and animals are utilising this whole body of water, the deep sea doesn't seem that deep anymore. 1,000 metres to me that no longer feels that it's out of reach. As a society, it's not something which is difficult to do. It's not challenging anymore. So it's about time we redefined what the deep sea was and changed it to 1,000 metres. So joining us today is the social media and squid legend, Jeff Day. So Jeff, welcome to the Deep Sea Podcast.
Thank you for having me, Alan.
So tell us a bit about yourself, because we actually don't know very much about you. You're someone we've come across basically by using Twitter. and you're obviously quite a big presence on there. And we thought it would be an interesting spin on this episode to speak to someone who's very much in that kind of environment. So just kick off with telling us a bit about you.
Sure. That's always something that's rather hard for me to summarize, but I'll give it a shot. A software engineer is my day job. I live in Houston, Texas. And I've always kind of been interested in the weird and deep sea life, but I never really got super deep into it until fairly recently.
So you're not a scientist then?
Nope.
That's amazing, because we were at some point trying to figure out exactly where you were, because we just figured your knowledge of cephalopods and deep sea stuff is almost encyclopedic. So we're thinking, well, where does this guy work? And we couldn't find you anywhere. So you're not a scientist at all. This is just a hobby of yours.
Pretty much. I guess I've picked up a lot via osmosis and from conversing with actual scientists.
Ah, that's brilliant. No, I love it. That's so cool. So you're obviously a big part of deep sea community on social media. And what is it about these platforms that you find so engaging?
There are a number of things. Partially, it's the kind of immediacy of it. A lot of us are just watching the dives as they happen. And for example, I'll be watching Nautilus and I'll see a Teningia and I'll tweet a bunch of expletives and then a clip of the squid itself right as it's happening. And also it's like a very easy venue for me to consume lots of information and find out a lot of different things from people who are highly specialized amongst a particular topic. And my brain kind of builds this map of topics to specialists. So it's always kind of fun for me to come across something and then figure out who the best person to ask about it is.
Yeah, because it feels like social media is now actually genuinely quite a useful tool for science in terms of sourcing rare observations or content or getting IDs from experts. And in the good old days, that wasn't possible. So it feels that social media is actually genuinely part of the scientific process now. We've certainly used it recently as well.
Yeah, I think there were actually a couple of papers that were published specifically from collaborations that occurred on Twitter. One of them I can think of off the top of my head is Derek Hennon, who studies centipedes and millipedes. Did a paper with a mycologist, or maybe it was a parasitologist, because they were looking at one of his photos and they noticed this extremely tiny parasite or fungus that hadn't been documented before, and just by a happenstance, and so they published on it.
Yeah, that's a good point. I think it's like it feels like there's now a bit of a grey area between the scientific community and citizen science, where it's actually both citizens, if you like, or non-scientific communities and scientific communities are meeting in the middle and actually being quite constructive. It's certainly in people like yourselves and others I've seen on Twitter who are watching these live feeds and pulling out images and actually doing a lot of the outreach on their own, rather than it coming from the scientists to non-scientists. I think that's a really interesting aspect of this.
Yeah, I was joking with somebody who asked a question on Reddit about some observations of like these specifically rare squid. And I was explaining to them how I came to know all this stuff. And I wound up, I think the sentence was, it occurred to me while I was writing this that it's maybe not exactly normal to have a mental Rolodex of toothologists and their relevant families of expertise and which social media platforms they respond the quickest on.
So you're documenting all this as well, right? I read somewhere that I think you said you were compiling every known observation of the Magnapinidae, the big fins. Is that right?
Oh, yeah. That how that came to happen is an interesting story in and of itself, because I know that you've spoken to the Magnapinna archive, and he and I randomly kind of connected because I was just posting random clips of Magnapinna that I was digging up when I first started getting into this, and he starts messaging me asking where I'm getting these and if I've seen a particular one, and eventually like he starts the Magnapinna archive channel, and I kind of give him the heads up whenever I ever come across a new one, which did just happen in the oddest way possible. I found a Magnapinna observation in the Jamstack archives I hadn't noticed before.
That's cool, because remember we did a podcast episode with Mike Vecchione, and he was talking about the value of rare observations and things like he would never dream of even applying for money to put together an expedition to go look for the big fin, right? That's not how you're going to get these observations. These observations will be happening by accident and by chance. And so, ROVs working offshore might come across one, a scientist in, Japan may see one. And over time, these will eventually become a data set. And I think somewhere in the middle of all that, it has to percolate through social media, and people like yourselves are bundling it up and saying, here you go. And that's how that type of science is done. There probably isn't a better way for doing it right now. That's just the way it is. How is it changing? Do you feel like since you got into this that the social media environment is changing for this type of stuff? And what are the best platforms for this type of observation sharing at the moment?
That's an interesting question. So I definitely started out on this on Twitter, and the science community on Twitter has been very strong. I think sort of in the last couple of years, people have looked for alternative platforms.
Yeah.
There's a fairly solid science community on both Mastodon and Blue Sky, but at the same time, they don't have quite the critical mass of people participating. I know that if I need an ID, I'll still tag people on Twitter because there are a bunch of people who are only on Twitter or who just respond faster there versus the other platforms.
Yeah.
I would say that the landscape has kind of changed in that, Twitter isn't the end all be all in terms of communicating with people on a very fast basis, but there's not really a solid alternative that's emerged as the next thing after that.
Yeah. So you're a squid guy then. So what is it that draws you towards the squid?
It's funny. I didn't start out as a squid guy. I actually started getting more into this because I wanted to learn more about Dumbo octopuses.
Mm-hmm.
But the further I got into it, the more I realized that footage of Dumbo octopods is not super common.
Yeah.
And there are only, 4 major families, and you can kind of get a handle on, the different species of each. But when it comes to deep sea squid, they're just astonishingly diverse, and they have the widest variety of just crazy body plans.
Yeah.
Like if you look at something like Magnapenta or Juvenateuthis, and then of course at the other end of the spectrum, you've got your squid-shaped squid like Philodoteuthis and stuff like that. And I don't know, the variety is just, I haven't gotten bored of it yet. There are just so many interesting, beautiful animals.
Yeah, no, I love it. Whenever we see a squid, there's great excitement. And a couple of years ago, we found the Dumbo octopus down at 7,000 meters. That was just incredible. It's just what a beautiful animal to find in such ridiculous deep depths. But one of the problems we sometimes have with squid is we do probably see them more than you would think, but quite often they're so fast, our cameras can't keep up. So you just have this like torpedo blur. The deeper we go, not the worse the cameras are, but they're certainly not the super high-end 4K, 8K stuff you see in some of the shallower stuff. So we're kind of at the mercy of what you can buy to go to those depths. And squid, I reckon, know that. So they just speed up. So we know we can never get a good shot of them. They're always eluding us. It's just that group of animals. So of all the squid down, what one do you think is the most underrated and deserves more recognition? Everyone's got that special one that you think, no. We need to get some PR behind this particular species.
I feel like a weird deep sea squid that doesn't get enough love would be the Juvenateuthis, because we've seen it twice. Once by Schmidt Ocean Institute in 2000, and NOAA came across it once in 2003, and they literally took footage out of the porthole of a submersible. And it's got this weird body plan. I think it's this sister group to Magnapenta, so it's got a similar weirdly exaggerated, like very skinny body, but very long tentacles, not as long as Magnapenta.
Yeah.
But it also has like the chirotoothed elaborate secondary tail, and it's just such a weird squid, and we've seen it so few times. Yeah, I would love to see more of those. They're so interesting.
Cool. Well, it's great talking to you, Jeff, and thanks very much for your time.
Well, thank you for having me. It was great talking to you, Alan.
That was a pressurized version of one of our longer episodes. If you enjoyed that and you would like to hear the full length episode, just match the episode numbers and you'll be able to find the full length version in the feed. Thanks for listening. We'll deep see you next time, and I abyss you already.